Is the exploration of Ullmannite-based thermoelectric materials. This is the content of my presentation. Firstly, research background and my research material and experimental results and calculation results and conclusion. This is an overview of industrial primary energy. The industrial primary energy, only 34% is used like this. Meanwhile, that of 66% represents a huge unused energy resource available worldwide. This is the temperature profile of industrial waste heat. The waste heat below 150 degrees accounts for a large percentage. So, some technology that can regenerate that waste heat into available energy is necessary. So, we focus on thermoelectric conversion. Thermoelectric effect enables a direct conversion from thermal energy into electric energy. This is a schematic picture of the principle of Sept effect. The temperature difference of the module like this generates the electric motive force by Sept effect. We can evaluate the thermoelectric performance by using figure of merit according to this formula. Rho is electrical resistivity, S is thermal power, kappa is thermal conductivity, K is absolute temperature. The good thermoelectric materials means low electrical resistivity and low thermal conductivity and high thermal power. The tellurium compounds such as bismuth telluride or lead telluride are well known as thermoelectric materials like this. The tellurium-free thermoelectric materials are required because tellur is rare. So we focus sulfide thermoelectric materials because sulfide is cheap, abundant, and non-toxic. Recently, reported sulfide thermoelectric materials tetrahedrite show that high ZT value shows. So we explore the new thermoelectric materials. Especially, we focus on sulfide material Ullmannite. This picture is the crystal structure of Ullmannite. Chemical formula is nickel, antimony, and sulfur, so including 3D transition metal as nickel. The crystal structure system is cubic, so it is high symmetric crystal structure. This study investigated the thermoelectric properties of Ullmannite and their substitution system, nickel 1-X, TRX, SDS, experimentally and theoretically. This is a sample synthesis. This is a condition of sample synthesis. The mixture of stoichiometric elements was sealed in an evacuated closed tube ample like this. And for mother material Ullmannite, heating at 780 degrees for 10 hours, and their substitution system case heating at 1000 degrees for 10 hours. After that, the polycrystal were obtained like that. Finally, the sample was shaped and cut for measurement. This is a condition of physical measurement. We checked the crystal structure Ullmannite by using a powder X-ray diffraction. Electrical resistivity is measured by four-probe method in PPMS ACT. PPMS means physical property measurement system like this. Some power S and thermal conductivity were measured by two-probe method in PPMS TTO. This is the temperature dependence of electrical resistivity for Ullmannite and their substitution system. This line is mother material, this line is iron substitution system, this line is cobalt substitution system. The law for all samples increase linearly with increasing temperature that show metallic behavior. The residual resistivity, which is constant value at low temperature, increases with TR substitution like this. The neutral impurity scattering is dominant at low temperature. The law is linear to T like this, which indicates that acoustic photon scattering is dominant at high temperature. This is temperature dependence of some power for Ullmannite and their substitution systems. This black line is mother material. This line is iron substitution system. This line is cobalt substitution system. The sign of S for nickel 1 minus X, TRX, SBS change from negative to positive with decreasing temperature, like this. Indicates that the whole contribution is dominant in the low temperature region. However, the epsilon contribution becomes dominant at higher temperatures. The sign reversal behavior reflects that the nickel 1 minus X, TRX, SBS multi-carrier system. It is consistent with the calculation results. The TR substitution decrease absolute value of S compared to that of Ullmannite, like this. We investigated the electric properties by using first principle calculation. We use software package OpenMX. OpenMX is based on density functional theory (DFT), non-conserving Schur potentials, and Schur atomic localized basis function. Calculation condition is like this. The electric dispersion relation and density of states and partial density of states are using K-grid 11. K-grid means the number grid of K space. The temperature dependence of some power S K-grid use 71. The S for Ullmannite is calculated from the temperature dependence of chemical potential mu according to this formula. This is the result of calculation, density of states. This is Ullmannite, this is cobalt substitution system, this is iron substitution system. Black line is total density of states. Color line is partial density of states. For Ullmannite, the density of states for nickel, antimony, and sulfur hybrid orbitals is dominant at Fermi level EF. The EF for nickel 0.75, TR 0.25, SBS are located in the wide conduction band and indicates the system is metallic. This result consistent with the experimental results. The band edge for TR substitution lift up and TR substitution like this. The density of states for nickel, TR, SBS, SV, and S hybrid orbitals near EF is split by TR substitution because like this. There it is. Because the crystal field is changed by the substitution. This is the electric dispersion relation. This is the Ullmannite and this is cobalt substitution system. This is iron substitution system. A whole pocket exists near the gamma and R position, which indicates that the Ullmannite is multi-carrier system. It is consistent with the experimental results. The band are split by crystal field with TR substitution, magenta and red band like this. This is a schematic picture, is the density of states. The degree of crystal field splitting is different from cobalt substitution and iron substitution, like this. Iron substitution is stronger. The TR substitution decreases the slope of density of states compared to Ullmannite, which indicates that the absolute value of S decreases with TR substitution according to this formula. It is consistent with the experimental results. The location of EF for cobalt substitution is different from that of iron substitution. And cobalt substitution location, the value of peaks like this, indicates the absolute value of S is small. Iron substitution between the value of valley and lower peaks indicates the absolute value S is medium, middle. This is temperature dependence of thermal power for calculation and experimental results. The slope of calculation ST curve DSDT higher than 100 Kelvin corresponds quantitatively to the experimental slope like this. However, the calculation cannot reproduce the positive contribution. So, further calculations, which includes the scattering process of conduction carriers, are required. This is my conclusion. And future work, Ullmannite is some power is not so large, so we expect that the band gap is modulated by the strong crystal field with further ion substitution. So the thermal power is enhanced according to this formula. We try to synthesize the further ion substitution of Ullmannite by the other method, molecular beam epitaxy method or Zolger method, etc. Thank you for your attention.
Influencing model with flat potential and massless scalar field is investigated. To get an inflationary universe, we have considered a flat region in which the potential is constant. To get the deterministic model of the universe, we assume that the selection parameter is constant. We find that spatial volume increases with time representing inflationary scenario. The Hubble parameter decreases with time and the Higgs field evolves slowly but the universe expands. The model representing decelerating and accelerating phase of the universe and isotropic. The result matches with recent astronomical observations. Now I came to introduction. The stage of exponential expansion of the universe is termed as inflation. The inflationary scenario is satisfactory solution to some of conceptual issues in cosmology and is not understood by the standard Big Bang cosmology. The inflationary scenario explains several mysteries of the modern cosmology like homogeneity, the isotropy, flatness of observed universe, and the primordial magnetic monopole problem. Booth introduced the concept of inflation while investigating the problem of why we don't see magnetic monopole today. Booth has also suggested that rapid expansion is due to vacuum energy and after inflation the universe is filled with bubbles. The inflationary scenario is also confirmed by CMB observation by Bassett et al. The notion of inflation is one of the best mechanisms at early stage of the universe to explain the flat and homogeneous and isotropic nature of the present day of the universe. In inflationary model, the universe undergoes a phase transition characterized by the evolution of Higgs field. The inflation will take place if potential V5 has flat region, and in this region the phi evolves slowly but the universe expands in an exponential way due to vacuum energy and suggestive extension. In this paper, we have investigated inflationary cosmological model in constant of quantitative space-time in potential V5 and deceleration parameter are assumed as constant. We find that Higgs field evolves slowly but the universe expands. The spatial volume increases with time, representing inflationary scenario. The models represent accelerating and decelerating phase of universe with match with recent astronomical observations. Metric and field equation. We consider quantitative in orthogonal forms is given by equation first. The Einstein field equation is given by equation second. The energy momentum equation is given by equation third. The conservation relation is given by equation 4 and the non-linear differential equation is given by equation 5, 6, 7, 8 and 9. We are interested in the inflationary solution, so flat region is considered. Thus we consider potential is constant. The scale factor for the line element first is given by equation 14 and to find the deterministic model of the universe we assume deceleration parameter is constant. And the scale factor is the equation is given by equation 16. The Hubble parameter, the expansion theta and the spatial volume are given by the equation 17, 18 and 19 and the scalar field is given by equation 20. Now I came to conclusion. The spatial volume increases with time representing inflationary scenario. The Hubble parameter is immensely large but decreases with time. The Higgs field evolves slowly, but the universe expands. The model represents descending and accelerating phase of the universe is beta greater than 0 and beta less than 0.
Massive string cosmological model with vacuum energy density and magnetic field. In general, in my research work, I take Biyani type first cosmological model, which is generalization of the FRW model, because FRW model are unstable near the singularity and can't explain the early stage of universe. So I take Biyani type first cosmological model. Our Biyani type first cosmological models are anisotropic and homogeneous. This anisotropy is due to presence of string. Here string is topological defect due to phase transition. But Biyani type first cosmological models is anisotropic due to presence of string, so as well as string will disappear, the anisotropy will disappear. In my cosmological model, I investigate my cosmological parameters in presence of magnetic field and addition of cosmological constant lambda. And cosmological constant lambda has discussed briefly. Now I will discuss that how magnetic field will affect our cosmological parameters. Now I will discuss my abstract. LRS Biyani type first massive string cosmological model vacuum energy density and magnetic field is investigated. To get the deterministic model of universe, we assume that shear sigma is proportional to expansion theta and as considered by chain and mu, where R is scale factor. We find that energy density, the particle density decreases with time. The vacuum energy density decreases with time, which matches with the astronomical observations. The model in general represents an isotropic space-time due to presence of string. Here I explain that what is string. String is the topological defects due to phase transition. Topological defects mean stable configuration of matter. The value of cosmological parameter decreases due to the presence of magnetic field, and model has quantized singularity at t is equal to 0. Now I am going to my mathematical work, that how does cosmological parameters will be effective by magnetic field, cosmological constant lambda and other mediums. Metric first is given by equation first. This is Biyani type first metric. Now I apply different condition on this metric and explain my results. Energy momentum tensor is given by equation second. Tij. This is the distribution of matter. Massive string condition is given by equation 4. Rho equals to rho p plus lambda in a co-moving coordinate system given by equation 5. The electromagnetic field described by equation 6 with equation 7. This equation is the mathematical representation of my problem, where Hi is the magnetic flux and epsilon ij kl Levi-Suter tensor, skl the electromagnetic field tensor, mu bar the magnetic permeability mod of Z, that of whole square equals to Hi and Gi is the metric tensor. We assume that magnetic field is due to an electric current produced along x-axis. Thus F23 is the only non-vanishing component of Fij, and H1 equals to not equals 0 and other coordinates will be 0. Maxwell equation given by equation 8. We also find that F1424 and F34 equals to 0. Due to assumption of infinite electrical conductivity, Martin's equation leads to H1 equals to H upon mu bar upon B square, and equation 9 and 10 leads to equation 10. No. given by equation 11, which is the mathematical representation of universe. And for the metric first, which leads to equation 12, 13 and 14. To get the deterministic equation in the terms of cosmic time d, we assume that shear is proportional to expansion theta as considered by Thorne. Thus we write A equals to d to the power n. This is due to shear sigma proportional to expansion theta. Equation 13 and 15 leads to 16. By equation 16, we get cosmological constant lambda equals to alpha b to the power minus 12 plus 1 upon 3, which is the cosmological constant lambda. Here we can see the behavior of the cosmological constant lambda, that how does it behave for our universe. Now equation 16 and 17 leads to 18. By this equation we get our values, it means we get our metric. Now equation 20 is the representation of my research work, where T is the cosmic time. Now discussion and conclusion. We find that energy density and string tension density are initially large but decreases with time. The spatial volume increases with time, representing inflationary scenario. The vacuum energy density lambda decreases with time, which matches with astronomical observations. The Hubble parameter is initially large but decreases with time. The model generally represents an isotopic space-time due to presence of string. The value of cosmological parameters decreases due to the presence of magnetic field. The model has point time similarity at t is equal to 0 given by Mikio. And these are references used in my research work.